Welcome to WikiPodcast. Think about the world around you. The sound of my voice filling this room, maybe the light reaching your eyes, even the signal that brings you your favorite radio station. What do those seemingly different things, sound, light, radio waves, what do they fundamentally have in common?
It's truly fascinating, actually. They're all manifestations of a single fundamental idea in physics, the wave. A propagating disturbance carrying energy, momentum, and information through space or, well, through a medium.
Okay, so let's take a deep dive into this. We've got some material here that really unpacks the world of waves. It's such a core topic in physics, especially, for sound and light. Our mission today is basically to pull out the essential insights, understand what waves are, explore the different forms they take, and see how there are sometimes strange, sometimes wonderful behaviors explain so much of the physical world.
And don't worry, this isn't about getting completely lost in complicated equations.
Yeah.
It's more about giving you the conceptual tools, the understanding of this really pervasive phenomenon, and appreciating its power, quickly getting you well informed.
Perfect. So let's start right at the beginning then. What's the core definition? What is a wave?
At its heart, a wave is a dynamic disturbance. Or you could say a change that propagates away from an equilibrium state.
Equilibrium being like a resting state.
Yeah.
A baseline.
Exactly, yeah. Imagine that perfectly still pond again. That's equilibrium. You toss a pebble in.
You create a disturbance.
Right, and that ripple spreading outward is the wave. It's a change from the flat surface, and it's moving across the water.
And this disturbance propagates, it travels. But here's a crucial point, isn't it? The water itself doesn't travel with the wave over, long distances.
That's absolutely key. Waves are these powerful carriers of energy and information, yeah, but they don't typically move the stuff they travel through. The water molecules in the pond might, bob up and down or maybe move in little circles as the wave passes, but they pretty much return to where they started.
So it's the pattern that moves.
Precisely. The pattern of the disturbance is what moves. Think of it kind of like a stadium wave. The people move up and down, but the wave itself travels all the way around the stadium.
That's a great analogy.
Yeah.
And waves often involve oscillation, right? A repeated movement.
Yes, especially for what we call periodic waves. They oscillate, they move back and forth repeatedly around that equilibrium value at a certain frequency, like a point on the surface of that pond bobbing up and down as the wave passes.
Okay. And we also hear about different kinds of waves based on how they propagate. You mentioned traveling wave versus standing waves.
Yeah.
What's the difference there?
Well, a traveling wave is pretty straightforward. The entire shape of the disturbance moves in one direction, like a pulse moving down a rope when you flip the end, or that ripple crossing the pond. A standing wave, however, is a bit more complex. It generally arises when you have waves moving in opposite directions that superimpose or, well, add up.
Like the vibration on a violin string, that sort of thing.
Precisely. When you pluck the string, waves travel to the ends, they reflect back.
Okay.
And these opposing waves interact in a way that creates a stationary pattern of oscillation. The string seems to vibrate up and down just in place, and there are specific points, we call them nodes, that don't move at all, and points in between called antinodes, where the movement is maximum.
And those nodes are fixed, like at the ends of the string.
Typically, yes. That's why it's called standing. The pattern itself doesn't travel along the string. A drumhead vibrating is another example, just in 2 dimensions.
Got it. So the core idea is this traveling disturbance carrying energy, but not the medium itself. And sometimes you get this stationary pattern twist with standing waves. Now let's look at the major types of waves we encounter in classical physics.
Right. The 2 big families, you could say, are mechanical waves and electromagnetic waves.
Mechanical waves. Okay, I'm guessing from the name, these need a physical medium to travel through.
That's exactly right. They rely on the mechanical properties of a material, could be a solid, a liquid, or a gas. Their propagation involves local deformations or changes in pressure, stress, strain, things that push and pull on neighboring parts of the medium, passing the disturbance along.
Like sound. Sound needs air or water or even a wall to travel through, doesn't it?
Sound waves are a perfect example. They're propagating variations in pressure and particle density. Other mechanical waves, think seismic waves rumbling through the Earth's crust.
Earthquakes?
Yeah, or surface waves on water where gravity is actually the restoring force pulling the water back down. Or, like we said, vibrations on strings like a guitar or piano.
Okay. And the other major type, electromagnetic waves.
Ah, these are incredible. They involve oscillating electric and magnetic fields coupled together. A really key insight here is that disturbances in these fields propagate as waves.
And the crucial difference from mechanical waves is you're going to say they don't need a medium.
Exactly. They don't need a physical medium. They can travel right through the vacuum of space. That's how light from distant stars or, radio signals from satellites actually reach us.
That's mind-blowing when you stop and think about it. Carrying energy across totally empty space. And visible light, that's just a tiny slice of this whole picture, right?
Just a tiny sliver. The electromagnetic spectrum is this whole family of waves, differing only in their frequency and wavelength. From the longest wavelength, lowest frequency, you've got radio waves, then microwaves, infrared, then our little window of visible light, then ultraviolet, X-rays, all the way up to these super high frequency gamma rays.
So they're all fundamentally the same thing.
Fundamentally, yes. Same phenomenon, just different energies, different frequencies. It's like different colors of the same light, but extending way, way beyond what our eyes can actually see.
It really makes you realize how much of the universe is just made of waves we can't even perceive directly. The material also briefly touches on some other types, like gravitational waves. That sounds different.
Yeah, and it just shows how pervasive this wave concept really is. Gravitational waves, predicted by Einstein and only recently detected, which is amazing.
Incredible, yeah.
They are disturbances in the very fabric of space-time itself. They propagate outwards from these huge cataclysmic events like colliding black holes. Then you've got fascinating waves in plasmas or even these chemical reaction diffusion waves that create patterns. The universe really loves waves, it seems.
Okay, so we have the definition, the different types. How do physicists actually describe these waves precisely? The material mentions mathematical descriptions.
Well, the power of physics lies in being able to model these things accurately, right? So we can describe a wave mathematically, usually as a function that tells you the disturbance's value at any point in space and any moment in time.
Okay, don't need the math itself, but the idea is it captures the wave shape and how it changes.
Exactly. It lets us predict how it will behave.
And a core principle here is superposition. That sounds important.
Superposition is absolutely fundamental, especially in simple, what we call linear media. It's the idea that when two or more waves of the same type arrive at the same point at the same time,
They just add up.
they just add up. The total disturbance at that point is simply the sum of the individual disturbances of each wave.
So if a crest meets another crest, they make a bigger waves. If a crest meets a trough, they can cancel out.
Exactly. That simple adding rule is the key to understanding really complex wave phenomena like interference, which we'll get to. The material also mentions wave families and differential equations.
Okay, that sounds a bit technical, but what's the conceptual insight there?
Okay, think about a musical instrument again, like an organ pipe or a guitar string. It can't just vibrate at any old frequency, can it?
No, you get specific notes.
Right. The physics of the system, its length, its tension, the medium inside it constrains it to specific allowed patterns of vibration. These specific discrete patterns are the wave families, or modes. For the organ pipe, for example, the sound wave inside can only form patterns where certain points, the nodes, are fixed. This leads to a specific set of possible notes it can play.
So the physical setup itself dictates the possible wave patterns.
Precisely. And differential equations are basically the mathematical rules that describe how these wave patterns must behave according to the fundamental laws of physics for that particular system. Equations like the wave equation or the heat equation,
Sure.
they aren't just abstract formulas. They translate physical principles like how energy moves or how pressure relates to force into constraints on how a wave must evolve over time and space.
Oh,
So the powerful insight is this. Physics gives us the rules, the equations that define all the possible valid wave behaviors in a given environment.
that's a great way to think about it. The equations are the rules the waves have to follow. Okay, let's talk about some special wave forms and key properties. The simplest one is the sine wave.
The sine wave is, the purest, most basic wave shape. It represents simple harmonic motion. Think of a pure tone in music, like from a tuning fork. And they're incredibly important because, remarkably, really complex wave shapes, like the sound of a whole orchestra, can be mathematically broken down into or built up from a sum of many sine waves of different frequencies. That's Fourier analysis.
That's amazing. You can build any complex sound just out of simple, pure tones.
Pretty much. It's a cornerstone of signal processing, acoustics, you name it. And sine waves have this unique property. If you add two sine waves of the same frequency, you just get another sine wave of that same frequency, maybe with a different amplitude, a different starting point, but the frequency stays the same.
Interesting. What about a plane wave? That sounds more abstract.
A plane wave is definitely an idealization, but it's a really useful model. Imagine a wave disturbance that's constant over an infinite flat surface, and that whole surface moves forward in a straight line.
Okay.
We use this to model waves when they're really far away from their source, like light from a distant star. By the time it reaches us, the wavefronts are practically flat, like planes. And for transverse waves like light, the oscillation is perpendicular to that direction of travel.
Right. We touched on standing waves earlier, like the violin string. Any more key ideas about them? Nodes and antinodes?
Yes, standing waves are really characterized by those fixed points, the nodes where there's no movement, and the points of maximum amplitude, the antinodes. They arise, as we said, from interference, usually due to reflection at boundaries. It's how musical instruments or confined spaces like organ pipes or flutes produce specific harmonic series of notes. They basically support standing wave patterns at particular resonant frequencies.
Makes sense. Okay, here's one that sounds a bit sci-fi. Solitary waves or solitons? What are they?
Solitons are fascinating. They're almost a bizarre type of wave in a way, unlike most wave packets, which tend to spread out or disperse over time.
Right, they lose their shape.
Solitons maintain their shape and speed as they propagate, sometimes over huge distances.
How? Why don't they spread out like other waves do?
This is a really cool insight. It's because of a delicate balance between competing effects within the medium they're traveling through. See, in many media, the speed of a wave depends on its frequency, that's dispersion, which we'll get to. This normally causes different frequency components in a complex wave to spread apart.
Okay.
But in specific nonlinear media, where waves can interact with each other in complex ways, there's another effect. A soliton is the special case where these dispersive effects and nonlinear effects perfectly balance each other out. It allows the wave to kind of self-reinforce and maintain its form. They're actually solutions to some very important nonlinear equations in physics.
That is wild, a wave that just holds itself together.
Yeah.
Okay, let's talk about amplitude and modulation. Amplitude is the height.
Amplitude is simply the maximum extent of the disturbance from equilibrium. Yeah, the height of the wave, essentially. It's directly related to the wave's intensity or energy. For sound, greater amplitude means louder sound. For light, greater amplitude means brighter light. Pretty straightforward.
And modulation, that sounds like radio.
Exactly. Modulation is how we encode information onto waves, particularly in communication. It involves varying a property of a carrier wave, like its amplitude or its frequency over time, to represent the information we want to send.
Like AM and FM radio.
Precisely. AM is amplitude modulation. You change the height of the radio wave. FM is frequency modulation. You change the frequency of the radio wave slightly. That's how the sound signal gets carried.
That makes the technology we use every single day much clearer. Okay, let's dive into how waves actually interact with the physical world. This covers a lot of familiar ground, I think. We already mentioned propagation, longitudinal versus transverse.
Right. Just to recap, longitudinal, the oscillation is parallel to the direction the wave is traveling, like the back and forth compression of air particles in a sound wave.
Okay.
Transverse, the oscillation is perpendicular to the direction of travel, like the up and down motion of a wave on a string or the oscillating electric and magnetic fields in light waves.
And sound in air is always longitudinal. Light is always transverse.
Sound in fluids like air or water can only be longitudinal, yes. Electromagnetic waves, like light, are always transverse.
Got it. And the material the wave travels through, the transmission medium, that matters too, right?
Oh, absolutely. The properties of the medium dictate how the wave behaves. Is it uniform, same properties everywhere? Is it isotropic, same properties in all directions? Is it linear, meaning do waves just add up nicely by superposition? Or do they affect each other? Is it bounded like that string fixed at both ends? These properties determine things like the wave's speed, how it reflects, how it refracts. Everything.
Okay, one interaction we see all the time is absorption, things soaking up waves.
Absorption is basically when the energy of a wave is taken up by the medium it's passing through. Often, that energy gets converted into other forms, like heat. A simple, everyday example is color. Why does an object appear red?
Because it absorbs the other colors.
Exactly. It absorbs most frequencies of visible light, but reflects or maybe transmits the red frequencies. The energy from the absorbed frequencies usually just warms the object up a tiny bit.
Then there's reflection, the bounce, like a mirror.
Reflection is fundamental. When a wave hits a boundary or an obstacle, part or all of it can bounce back. The classic law you learn is that the angle the incoming wave hits the surface at the angle of incidence equals the angle the bounced wave leaves at the angle of reflection.
Like bouncing a ball off a wall.
Precisely. Or light off a mirror, or sand echoing off a cliff face.
And refraction, that's the bend, right? Like the classic straw looking bent in a glass of water.
Refraction, yeah. It occurs when a wave changes speed as it passes from one medium into another. This change in speed causes the wave to change direction, to bend. There's a rule called Snell's law that describes this bending precisely, and the amount of bending depends on something called the refractive index of the two materials involved. The straw looks bent because light slows down and changes direction when it goes from the air into the water.
Okay, diffraction is the bending around obstacles. I always think of hearing a car coming around a corner before you actually see it.
That's a perfect example. Diffraction is the phenomenon where waves spread out or bend as they pass through an opening or around an obstacle. It's most noticeable when the size of the opening or the obstacle is similar to the wavelength of the wave.
Oh, okay.
So long wavelength sound diffracts really easily around everyday objects, like corners of buildings. Short wavelength light diffracts much less noticeably in our everyday experience, unless it's going through a very, very narrow slit or around a sharp edge.
That explains why sound seems to bend around corners, but light mostly travels in straight lines for us.
Exactly. It's all about the wavelength relative to the size of the obstacles.
And interference brings us back to that superposition idea again.
Indeed. Interference is the pattern that emerges when two or more waves overlap and superpose when they add together. Where crests line up with crests, you get constructive interference. The amplitudes add up, resulting in a larger amplitude, think louder sound or brighter light.
Okay.
Where crests line up with troughs, you get destructive interference. The amplitudes subtract, resulting in a smaller amplitude or sometimes even complete cancellation, quieter sound, or darker areas in a light pattern.
And this causes, like, noise-canceling headphones or patterns on soap bubbles.
Precisely. Noise-canceling headphones generate sound waves that destructively interfere with incoming noise. The shimmering colors you see in soap bubbles or oil slicks, that's constructive and destructive interference of light waves reflecting off the inner and outer surfaces of the thin film.
Fascinating how that simple adding rule creates such complex and beautiful patterns. Now, polarization, you said that only applies to which type of wave again?
Only to transverse waves. Like light. Polarization describes the orientation of the oscillation. For light, the electric field can be oscillating vertically or horizontally, or at some angle in the plane perpendicular to the direction of travel.
So, what does that mean practically? Sunglasses.
Polarizing filters, yeah, like in polarized sunglasses, they work by blocking light waves that have a specific polarization orientation. Glare, like light reflecting off water or roads, is often strongly horizontally polarized. So polarized sunglasses block this horizontal component, reducing the glare significantly.
Clever. Okay. Dispersion is another way waves can get dispersed, spread out.
Yes, dispersion means that the speed of the wave actually depends on its frequency. So if you have a wave that's composed of multiple frequencies, like white light is composed of all the colors, those different frequencies will travel at slightly different speeds through the medium. And because they travel at different speeds, they spread out.
The prism, splitting light into a rainbow.
That's the classic example. White light goes into the prism, which is a dispersive medium for light. The glass causes each color, each frequency, to travel at a slightly different speed. This means they bend by slightly different amounts as they enter and leave the prism, spreading them out into the visible spectrum, the rainbow.
That's the physics behind rainbows.
Yeah.
Amazing. And finally, the Doppler effect, the changing pitch of a siren as it passes you.
The Doppler effect, yeah. It's the apparent change in the frequency of a wave that happens when the source of the wave and the observer are moving relative to each other. As a sound source, like that ambulance siren, moves towards you, the sound waves effectively get compressed, they reach your ear more frequently, so you perceive a higher pitch.
Right.
As it moves away, the waves get stretched out, reaching you less frequently, so you hear a lower pitch. This principle is used all over the place, from police radar guns measuring speed to astronomers measuring the speed of distant galaxies based on the shift in their light.
Wow, that's a huge range of interactions then. Reflection, refraction, diffraction, interference, polarization, dispersion, Doppler effect. It really is incredible how many everyday phenomena and scientific tools boil down to how waves interact with matter and with each other. Our material also mentions different wave velocities, phase and group.
Yes, that's a slightly more subtle point, but important. Phase velocity is the speed at which a point of constant phase on a single ideal wave moves, like how fast a single crest travels along.
Okay, the speed of a point on the wave.
Right. Group velocity, on the other hand, is the speed at which the overall shape or the envelope of a wave packet moves. A wave packet is like a localized burst of waves made up of many frequencies. Now, the insight here is that the group velocity is typically the speed at which energy and information are actually transferred by the wave.
And they can be different.
They can be different, especially in those dispersive media we just talked about, where wave speed depends on frequency. In dispersion, different frequency components within a complex wave packet travel at different phase velocities. This causes the wave packet to spread out. In such cases, the group velocity, the speed of the overall packet, can be different from the phase velocity of the individual waves making it up. And usually it's the group velocity that tells you how fast the information in the packet is actually traveling.
Interesting. So the pattern speed could be different from the energy speed in some cases. Let's just briefly revisit mechanical and electromagnetic waves with some specific examples from the material, just to ground it.
Sure. For mechanical waves, like waves on a guitar string, their speed is determined by the tension in the string and its mass per unit length, how heavy it is.
Which is why tightening a guitar string raises the pitch, right?
Yeah.
You're increasing the wave speed.
Exactly. For sound waves, the speed depends on the stiffness, technically the bulk modulus, and the density of the medium it's traveling through. Sound travels faster in solids than in liquids or gases, generally because solids are much stiffer.
Okay.
And seismic waves, like the P waves, which are longitudinal, and S waves, which are transverse, that travel through the Earth after an earthquake. These are mechanical waves. Studying how they propagate and reflect off different layers inside the Earth is crucial for understanding our planet's internal structure.
Right. And electromagnetic waves, as we already covered, propagate at the speed of light, a fundamental constant predicted by Maxwell's equations linking electricity and magnetism.
That's right. Oscillating electric and magnetic fields perpendicular to each other in the direction of travel, self-sustaining, and moving at that universal constant speed c in a vacuum.
Okay. Finally, let's just touch on some concepts that really push the boundaries of our everyday intuition. Things like quantum mechanical waves and gravitational waves again. De Broglie waves. What's that about?
Ugh, this is where physics gets truly mind-bending. Louis de Broglie proposed, and experiments later stunningly confirmed, that all particles, even things we typically think of as solid little objects like electrons or protons or even whole atoms, they all have a wave-like nature. There's something called the de Broglie wavelength associated with any particle, and it's related to its momentum. The more momentum, the shorter the wavelengths.
Wait, so an electron isn't just a tiny ball orbiting an atom, it also is a wave.
In the quantum world, yes. It exhibits both particle-like and wave-like properties. This wave-particle duality is a fundamental, if weird, insight of quantum mechanics. We often describe particles mathematically using wave packets, which are basically superpositions of many different waves that, when you add them all together, are mostly zero everywhere except for a small region in space. This effectively localizes the particle, but still retains its underlying wave properties, like interference and diffraction.
Wow, that's a concept that definitely takes some pondering. And gravitational waves. Just to be clear, not the same as gravity waves in fluids, like on a pond.
Correct, totally different scale. Gravity waves in fluids, like ripples on a pond or ocean swells, are disturbances on the surface where gravity acts as the restoring force, pulling the water back down. Gravitational waves, as we discussed briefly before, are far more profound. They are ripples in the curvature of space-time itself, predicted by Einstein's general relativity.
Generated by massive things.
Generated by extremely massive accelerating objects, like pairs of black holes or neutron stars merging. They create these propagating distortions of space-time geometry itself, traveling outwards at the speed of light. Their recent detection was revolutionary. It opened up a whole new way of seeing the universe using gravity instead of light.
Incredible. We literally started with a pebble in a pond, and we've ended up talking about ripples in space-time and fundamental particles behaving like waves.
It really highlights how incredibly powerful and unifying the concept of a wave is throughout all of physics, doesn't it? From the sounds you hear every day and the colors you see, to how your radio and Wi-Fi work, how musical instruments make their specific sounds, how geologists study the deep earth, and even understanding the fundamental nature of reality at the very smallest and the very largest scales.
It absolutely makes you look at the world differently. You start seeing the unseen waves everywhere and recognizing how these interactions we talked about, reflection, interference, the Doppler effect, shape almost everything we experience.
Absolutely. Once you start thinking in terms of waves, you really do see them everywhere, maybe in the patterns of sand dunes, the way light hits a surface, the way sound fills a room or echoes.
So what's the big takeaway here? Perhaps the most provocative insight from this deep dive is just how much of the universe's activity, from the faintest whisper of a radio signal coming from across the galaxy to the absolutely thunderous collision of black holes, is carried by waves. Waves that are totally invisible to our everyday senses, yet are governed by the same fundamental principles as the light and sound we do experience.
That's a great way to put it.
And the idea that even fundamental particles possess this wave-like nature. It's just a profound reminder that reality is often much stranger and more interconnected than it appears just on the surface.
There's always more to explore, of course, but understanding these basics really does give you a powerful lens through which to view the physical world.
Thanks for listening. Write us your opinion in the comments on which specific wave behavior may be reflection, interference, or perhaps the Doppler effect you find most fascinating, or notice most often in your daily life. Subscribe to the channel to help more listeners reach our deep dives. Thank you and have an amazing day.